we present EventHands, the first method for 3D hand tracking from a single monocular event camera. Compared to conventional RGB cameras, which record synchronous absolute brightness images, event cameras react on brightness changes on the pixel level and report them asynchronously. This results in lower data throughput and enables hardware support of high temporal event resolutions of down to 1 microsecond. Event streams thus do not suffer from motion blur, even for swift motions and changes in the scene. This makes them well suited for capturing rapid motions of hands in action and allows EventHands to estimate poses at 1000 Hz in real time. EventHands is a learning-based technique that tracks hands using an event camera. To efficiently learn from asynchronous 1D event streams, we convert them to a new accumulated representation, which we call locally normalized event surfaces, or LNES, and which is more suitable for visual machine learning tasks. In contrast to naive images of collapsed events, such as event frames or event count images, where temporal information is lost, LNES stores normalized timestamps of the two polarities in two separate channels to preserve the ordering and direction of brightness change. The length of each LNES window is 100 milliseconds, and we overlap the windows by 99 milliseconds to achieve an effective temporal resolution of 1 millisecond. To support inference at this high speed, and also high prediction accuracy, we choose to use the ResNet 18 backbone. We train our method to map LNES input to a 12-dimensional output space that encodes the hand pose and the global translation and rotation of the hand. The first 6 parameters represent the first 6 PCA coefficients of the parametric Mano hand model. The remaining 6 parameters encode global hand translation and rotation in axis angle representation. To stabilize per-frame estimates temporally, and to make the method robust to noise, we apply a Kalman filter on the network predictions. As there are no available datasets for 3D hand reconstruction from event streams, we developed a new GPU event stream simulator to generate such a dataset. Our event stream simulator renders synthetic images of hands and simulates per-pixel brightness changes, which trigger synthetic events. We generate data originating from scenes with Mano hands with diverse appearances and poses, observed in a variety of backgrounds, lighting conditions, fields of view, and event thresholds. In total, our dataset contains 100 hours of simulated data, with annotations at over 360 million discrete time steps. To account for additional data variations and reduce the domain gap between real and synthetic data, we perform extensive augmentation of the generated event streams. This includes simulating event noise, varying window length to simulate different hand speeds, and swapping random pixel polarity to simulate different scene appearances. To evaluate our predictions and compare against RGB methods, we propose the first event stream benchmark with images from synchronized 500 frame per second RGB camera videos. The benchmark contains 357 frames with 7 manually annotated 2D key points at each frame. These consist of the 5 fingertips, the middle MCP joint, and the hand wrist. These 2D annotations on both the event stream and the RGB images are verified and corrected by multiple annotators. For the ease of visual assessment, all of the sequences shown in the next 2 sections would be slowed down by 16 times. Now we show experimental results. Note that we render the predictions using the mean hand shape for visualization purposes. Please ignore the motion of the arm, as its prediction is outside the scope of this work. We render the arm so that the hand is not floating in the air. Compared to existing RGB methods, EventHands can predict poses at much higher temporal resolution while having much smaller data throughput. Even in scenarios which fulfill the assumptions of the RGB methods well, the input images are often blurred due to fast hand motions, which causes erroneous and less accurate predictions. The method of Buchheimer et al. Often defaults to the Mano mean pose when the input is too blurred. The method of Su et al. Does not predict the global translation of the hand, which is important for fast motions. Most commodity depth cameras produce corrupted depth maps for fast motions, and similar to the RGB cases, existing depth-based methods cannot handle these corruptions. Here we show our hand pose predictions from other views to assess the quality of predictions in 3D. Our LNES representation allows for very long window sizes, such as 300 milliseconds, without significant degradation of the prediction quality. We find that a window size of 100 milliseconds leads to the highest accuracy while maintaining event history long enough to capture natural hand motions without artifacts. We also find that both timestamps and polarities are expressive reconstruction cues preserved by our LNES representation that improve the overall accuracy over the naive method, which loses temporal information within a window. This is especially true when longer event windows are used. Even though we use long, densely overlapping LNES windows, we find that on real data, Kalman filtering is essential for high accuracy and temporal stability of the results. Now we show more results of our method. Here we show more results of our method, as recorded in a live demo. EventHands is also robust to outlier events generated by small objects while interacting with a hand, as showcased in this live demo example. Although our method targets settings with fast motions, it also works for slower motions. In low light conditions, hands cannot be tracked by RGB methods as they are barely visible in the image. However, our method generalizes to low light settings, since event cameras record the relative brightness of the scene. EventHands supports different arm poses in the view with respect to the camera. Here, we show results on real data from a model trained on hands coming from the bottom. Our method is ideal for tracking the rapid hand motions that occur while playing musical instruments. Our dataset, the simulator, and our 3D hand pose estimation method will be released for research purposes. Thank you for watching.